Welcome to the introduction of this new chapter about magnetism, and we are going to start off with looking at magnetic force and what it is. Now, magnetic force is something we use in day-to-day life quite often, sometimes in quite obvious applications, such as magnetic clasps, compasses, locks, like I've said here, refrigerator magnets, all very obvious. However, there are also a few other applications that use magnetic force that you may not have thought of before. Most electric motors used in hair dryers, vacuum cleaners, but also headphones, speakers, etc. They all use magnetic or electromagnetic force. More recently, a rise in electric cars and electric bikes. They are all possible because of electromagnets. Now, when we're talking about magnets, we'll be talking about them in two very broad categories: permanent magnets and electromagnets. A permanent magnet is a magnet that will always have its magnetic properties. You can't turn it off and on. It is bound to the material itself. Electromagnets, of course, require electricity, require current and voltage in order to be turned on. The major advantage, of course, being that you can turn them off. Regular magnets can sometimes be a bit of a hassle to work with because they stick to any, well, not any, but some metals at least. Now, when we look at the magnetic force between two permanent magnets, when we're talking about magnets, we will always state them as having a north pole and a south pole. In general, the north pole tends to be painted red. So if we're going to be doing any exercises from now on, always assume that the north pole is painted in the red color. This color is just paint, really. It doesn't really indicate that the entire left side of this magnet is a north pole and the entire south side of this magnet is a north pole. It's just an indicator in this case. Now, two very common magnets we'll be using in this chapter will be both the bar magnet, represented here. It can be round, it can also be sort of a square or rectangular shape, I should say. And then horseshoe magnets, who have two parallel legs, essentially. This can be round, it could be more, blocky, as you see here, but that doesn't really matter. The interesting part about the horseshoe magnet is this zone in between both of its legs in this case. Now, two magnets, they can either attract or repulse, same as we saw when we were studying Coulomb's laws, but please do not make the mistake of referring to these as the positive and the negative pole. That is not what we do with these. And the rule is quite simple. If you've got two of the same poles, they will repel, whether it's north or south pole, and if it's opposite poles, south and north, they will attract in this case. Now, there's one small thing that I have to say. This course is, of course, copied from books in Dutch and said would be the south pole, south pole in this case. You can use an S if you so desire. Now, if we look at the magnetic force between a permanent magnet and any other object, there's not a lot of them that will interact with a magnet. In fact, it's only a handful of them, and those are called the ferromagnetic metals. So, not all metal, just those ferromagnetic ones. And what are they? Those are iron, cobalt, and nickel. You do have to know those three. Now, can also be alloys, meaning mixes of metals, containing one of these three in this case. Now, if you get those ferromagnetic objects, they will become temporarily magnetic when they are approached by a permanent magnet. And this is called that temporary becoming magnetic influence. The ferromagnetic metal will become influenced by the magnet and will become magnetic in such a way that it will lead to attraction only. You will never have a ferromagnetic metal that will suddenly start repelling permanent magnets, because the polarity that is created inside of your ferromagnetic metal is dependent on the pole facing that metal in this case. Now, magnetic influence is not blocked by non-ferromagnetic metals like paper, aluminium, or anything along those lines. So you do have to be careful because your own hands are not ferromagnetic, and when they get stuck in between a metal and one of those very strong magnetic metals, that can lead to injuries. Now, what makes these ferromagnetic metals so special? Well, they have small areas called Weiss areas. Now, the print itself might not be that obvious, but under normal circumstances, meaning there are no magnets nearby, which is situation A, and situation B is there is a nearby magnet, and that nearby magnet, in this case, is represented by a magnetic field vector B. We'll be talking about this later in the future. Now, under normal circumstances with no magnets nearby, all those magnetic Weiss areas in the metal, they're just scrambled. They're all facing different directions, meaning there is no net magnetic field. This substance does not behave magnetically. However, these Weiss areas will start twisting to all face the same direction, or at least most of them will, and they will follow the magnetic field along that is created by your nearby magnet, and that's how they become, temporarily, magnetic. When that other permanent magnet is taken away, this highly ordered orientation of the Weiss areas will disappear, and it will go back into its scrambled state after a while when you remove the magnet. It's not instant, as I've shown you in our demonstrations during class, but it will happen over time and fairly quickly. Now, one of the first applications that we had below is the Earth as an actual magnet. It has a permanently magnetic core in its case. Now, historically, it was the compass that led to a major revolution in the world exploration. If you take a magnetic needle, like it's a small, thin strip of magnetic material, and you put it in free suspension, which means it is supported by only a needle point of its own, or just on the surface of water, it will point with its north pole to the geographic North Pole. This was a bit of a historical error, however, when you think about it. Why? Well, the same poles should repel in this case. This means the geographic north has a magnetic south pole in its location. So there was a historical error where they thought like, okay, well, if you take, it's always the same side of the magnet pointing towards the North Pole. Let's call this the North Pole of the magnet. However, later on, they discovered that north and north should repel. So in this case, there was a bit of a mistake there. Now, the Earth has its own magnetic field, and it is also needed to deflect solar winds. I will be linking you a video from the University of Oslo that explains these northern winds and how they are created. Now, essentially what you need to know is that the sun creates these solar storms, and these solar storms create highly charged magnetic particles that will emit light, and those are hurled into the universe, and they come barreling down to Earth, but they will be deflected by the Earth's magnetic field. And how this works is explained in this video that I will be linking to you soon. I'll put the link into the video description so you can check that one out for yourself. Now, Once you've seen or talked about or looked at this video, you can report back for part 2, where we'll be talking about the different magnetic fields that we will be using in the rest of our class, which is based on these northern lights. I will see you for that next video.